And here we go. We have liftoff.
Propulsion continues to be nominal.
R68 chamber pressure looks good.
Following up. Roger, roger, Atlantic.
Water towers fly! Yes!
Tango down to nominal.
Flight downside FD off. Bring in FD off. Off. It's orange!
45! Oh my god! Oh my god!
Decollage.
What is it?
Put that in the big bag, you know.
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
This methane will be igniting with the flare, correct?
Yikes. You bet. We don't need any more of these.
Hello and welcome to a very special episode of NASA Spaceflight Live. It's an interview show today, and I'm Jack Beyer, your host for today for NSF. But who cares about me? We have a very special guest, Mr. Tom Mueller. Tom, do we have you? And hopefully I'm pronouncing your last name right.
Yes, Tom Mueller. Great to be here.
Excellent. Well, we generally have a pretty technical audience here at NSF, but just in case people are tuning in and don't know the rocket engine wizard that you are, how about we just have you do a little bit of an elevator pitch, kind of, where you came from, what you're doing, and we'll jump into some questions.
Sure. Yeah, I grew up in a small town in northern Idaho, became an engineer, moved to California because I wanted to work on rockets, ended up working on rockets, started my rocket career at TRW, which is now Northrop Grumman, in 1987. Was there 15 years. Where at the end of that stint there, I was the manager in charge of all rocket engine development at TRW, and that's when I met Elon, and we started SpaceX, and I led the development of the propulsion systems for the Falcon vehicles, Falcon 1 and Falcon 9, and also Dragon vehicles, including the Draco, which there's one right there behind me, a little Draco engine. And I also worked a lot on Starship in the last 5 years I was there. And when I left, I retired from SpaceX in 2020, and then I started Impulse Space soon after. And having worked on Starship and being a real believer in Starship, I realized that here's a vehicle that's going to fly often, fully reusable, and it's going to be taking over 100 tons to LEO every time it flies. And I just thought the real opportunity now is going to be to move that cargo around in space. It's going to be able to take really allow a lot of different things to end up in low Earth orbit. And a lot of those things are going to go to different orbits or to higher orbits. So that was the reason I started Impulse Space.
Makes sense. And of course, this is NASA Spaceflight Live, so we are doing the standard thing. If you guys have questions, throw them in the chat. Adrian is also on today's call, and we'll be wrangling y'all's questions. So we'll just jump right into it. But really quickly, Tom, I have to ask, that Draco that's behind you, has that been flown? Has it been tested? Has it been fired?
It flew in space. Yeah, it flew on. I actually have a note from Dean Ono, my Draco guy, somewhere. I think it was CRS2, and yeah, I actually have the number. I need to make a plaque for it, like the number of pulses and all that. But yeah, it flew. Then it was changed out, and I ended up with it. Pretty cool.
Amazing. Well, that's quite a shelf accoutrement to just have in the background. Pretty nifty.
Yeah, one of my favorites.
Very cool. All right. Well, a little bit of a Homer Hickam vibe from you in terms of growing up in a working family and in Idaho and messing with model rockets from an early age all the way up to where you are now. That's pretty nifty. I
actually have made that connection before, having met him and living the movie and read the book. if you take his story and just change mining into logging, it's kind of the story of my life, because there were times that my dad wanted me to be a logger, because I did actually put myself through college by working as a lumberjack during the summers in Idaho. And there's one time when it was a tough year for the environment, for the economy, and my dad said, are they really hiring engineers? Maybe you should become a logger. Look how much money you're making. And it's kind of like the Homer Hickam story where his dad wanted him to be a miner. I actually went to the International Science Fair, my first trip to LA back in '77 when I was in high school, for a science project that I did. I didn't win anything like he did, and I didn't meet anybody famous, but it was very similar stories. Pretty cool.
Yeah, that's awesome. I think a lot of people can identify with your family wanting to sort of pull you one way, and yet you have grander designs. So neat. Let's see here. I do want to start off and just ask you. You're a fellow LA resident, is that correct?
Yes, I live here in Manhattan Beach.
Which coast is the best coast?
The West Coast is the best coast. I've never even really been to the East Coast.
The audience can't see it right now, but Adrian just did a face palm. So thank you for answering the question correctly. Cool. So let's just jump right into it. You have designed so many rocket engines. I mean, the Merlin, you were involved early on Raptor. You were talking about the Draco. What was it? The TR. Oh gosh,
106.
106. I knew there was a 6 and a 0 in there, which sort of morphed and parts of it became Merlin. Do you have a favorite rocket engine? I know that might be like asking you to pick your favorite child. It doesn't even have to be a rocket engine you design, but like, do you have an engine where you sort of look at it and you're just like, man, that is a beautiful engine?
Yeah. Well, I should say an impulse engine, just to sell my own brand, but my favorite's got to be Merlin. It's like unbelievable. Like, how many times has Falcon 9 flown without failure? Multiply that times 10, because there's 10 Merlins on every Falcon 9. Over 250 times. There's over 2,500 times without failure. So it's just an unbelievable engine. I mean, like I've said before, that's impossible. There's no way to fly an engine 2,500 times without failure, but here it is. It's really an amazing engine. Really, really proud of it.
Yeah, absolutely something to be proud of. Workhorse is a term that gets thrown around quite a lot, but I don't know any situation in which it would be more apt than this one.
I used to compare it to the small block Chevy because it was cheap and efficient and reliable. I think it still applies.
There you go. Yeah. So, founding employee of SpaceX along with Elon, what is it? And now you have a new company, Impulse. What is it like to sort of grow a company like that from just basically bare soil? Do you relish that? Is it challenging?
It's every emotion that exists. It's very difficult. It's a lot of new things that I didn't do before. When I was, I was at SpaceX as a startup from, a team of we started with 3 of us, and then Hans joined within a couple months later, so there was 4 of us. But anyway, it was just very, very small and grew pretty slowly at first. But I wasn't running the startup. I was just head down developing the engine. We got to a Merlin burn of just the TCA, the thrust chamber assembly and injector, in less than a year, and we got to a turbopump test in about a year. So I was just up to my eyeballs with that. So I wasn't really involved at that deep in the nuts and bolts of running a startup. So I'm learning a lot, running a company as a CEO.
Got it. So Impulse, you are developing space tugs because with a whole lot of upmass that's coming from all of the impending heavy lift vehicles that are coming online, there's going to be a lot of objects in orbit that sort of need positioning. Is that a fair elevator pitch for Impulse?
Yeah. Yes. I think it seems like we're in the right place at the right time and trying to fit our product into this perfectly into this market. Our products. Yeah.
Excellent. Adrian, do we have any viewer questions that we want to jump into right off the bat before we move on? Oh, you might be muted, buddy.
That would never happen. That would never happen. I would. The first question I would ask here is regarding actually the propellants you're now using at Impulse Space. What drove your decision there to arrive at the propellants you're now using? And like, for example, for space transport, there's often also hydrogen mentioned. So why did you went now with methane, for example, for Helios? So
People ask me if there was anything I would change going back to the original architecture of Falcon 1, which of course then that architecture led to Falcon 9. And the thing I would change would be not to use RP1, but to use methane. I think methane is the correct propellant. Everybody's using it these days, and it's the cheapest hydrocarbon fuel, and it has great performance. I'm the one that did the study, when I was propulsion CTO at SpaceX. Starship was originally a hydrogen vehicle. It was LOX hydrogen, and I kind of found out about the Sabatier cycle. And if you have hydrogen on Mars and the carbon dioxide that's 95% of the atmosphere of Mars, you can make methane for just about for free. Actually, you get some energy back and some water back when you do it, and you end up with 8 times as much propellant. So for every pound of hydrogen you convert, you get 8 pounds of methane. So I looked at that, and I told Elon, I said, it takes half the power, so it's really half the cost to bring that back. And then I looked at on Earth, and it's really half the cost of hydrogen. So you're buying a lot less hydrogen because it's the mixture ratio run at is much higher ox to fuel, but the cost of hydrogen is so high it's still twice as expensive as methane. So my job was like one of the first things he asked me when I became propulsion CTO was size a vehicle to take 100 tons to Mars. So I sized it, and actually it was actually after I switched it or convinced him to switch it to methane, it was the same size pretty much as the current vehicle. I had 3,000 tons of propellant on the first stage and 1,000 on the second stage. I think they've increased the first stage quite a bit, but it's still about the same size vehicle that I sized back in 2016 or whenever that was. And ever since then, it's just like, this is the right propellant. Like RP1 is expensive. It's an oil. It's a light oil, so it doesn't go away. It's very hard to evaporate it, so it's always there. It leaves soot everywhere inside the chamber and inside your your fuel-rich cycle. It sits up your nozzles and your injectors. So it's kind of miserable to work with. Whereas methane is a better coolant, and it goes away, and it doesn't make soot. That's why you get that beautiful blue flame like you're showing there, because there's no soot emissions. And it just evaporates. It doesn't seep across the seals in the pump and get into the oxide. It's cryogenic, but you're already dealing with a cryogenic. You just basically use the same valves that you use for the liquid oxygen, the same hardware. So you've already solved the cryogenic problem, so you might as well have them both. And then if you're doing on an upper stage, or like Helios, now you have 2 propellants that are much the same temperature, so that on a long coast you don't have like the heat from the fuel, like when you have RP1, conducting across the tank and boiling off your oxygen. So this in every way, really, except of course you take a little bit of a volume hit, so your rocket's a little bit bigger with methane. But I think in almost every other, and it's cryogenic, but every other way, I think it wins. And that's why everybody's using it now. Everybody's gone to it.
There's actually, I'm glad we are showing this test right now, because there's a very related thing I always wanted to ask you, and that is, we have seen different liquid methane engines at this point. Some of them are more orange-bluish. We have seen Raptor, which initially was very orange-bluish, and now we see, for example, Raptor here in very blue, and we have also seen BE4 in very blue. What do you think, like, what's causing these massive differences in color in the methane engines?
I think People think it's a mixture ratio. I doubt it's a mixture ratio because 3.6, 3.5 is almost always where you optimize with these propellants. It's, as you change the nozzle size, it moves a little bit, but not that much. I think if you have, like if you have a coating inside the engine, you should get like a trace amount of some particulate. Or if you're firing near the ground and you have dust, it colors it because once you entrain any particles, they glow. And I also think, on that Vulcan flight, I think when you have really bright exhaust from solids, it may be the way you contrast your cameras gives you that really beautiful blue that you don't necessarily see like on the ground test. Like right there on that shot. So you're entraining dust. So look at how orange it gets towards the end.
Yeah.
And look at the bottom of the plume is brighter than the top because you're entraining particles there. So that's my explanation.
Love it. Thank you.
Okay.
You've made a lot of nerds very happy with that explanation. We greatly appreciate that. If you can see our back channel right now, it's a whole bunch of really nerdy friends of mine all rejoicing. So thank you for that. So let's talk a little bit about Helios. That is your coming space tug, right?
Yep.
And you've already launched a vehicle called Mira on Transporter 9, if I'm not mistaken.
Right. Yep. In November, Mira went up. It's flying right now. It's going to do a burn in 25 minutes.
No big deal.
So in 25 minutes, I'm going like this. Yeah.
Very cool. So, okay, let me see if I can put a fine point on this. Elon is very much about getting to Mars and making humanity multiplanetary. Jeff is very much about moving heavy industry off Earth and into orbit. Is it fair to say that you're kind of a mix of the two in terms of your philosophy for what we should and could be doing in space, in terms of, yeah, let's go to Mars and let's make humanity multiplanetary, but let's also sort of protect our planet by moving all of this horrible stuff out into orbit if we can?
Yes, I'm all of the above and anything else. We're willing to do, like we've got a Mars lander. I'd love to do a lunar lander. I want to go to the outer planets. I love that as soon as we announced, the spec on Helios, that Scott Manley and others are already looking at this thing as how to get interplanetary probes out there. Would love to do things like that. I just want to expand like SpaceX and others, developing reusable stages and reusable vehicles have greatly reduced and increased the capability of getting to low Earth orbit. But I don't think there has been a great step in reducing getting everywhere else, to high energy orbits. Like if you think about, getting to LEO and compared to GEO, it's like 100 times further. Call LEO 360 kilometers and GEO is 36,000 kilometers. It's just there's just a lot of energy to get up there. And once you get to GEO, you're pretty much just a few more, hundreds of meters per second, and you're just about anywhere in the inner solar system. So we want to develop an efficient way of getting out from LEO outward.
I love it. I always lament the fact that we only have so much information from all of our probes. Like every planet should have probes going to it. Every moon of every planet should have probes going to it. I just have this desire to learn about our place in this solar system as much as possible, and a high energy upper stage or space tug is sort of exactly what we need to accomplish something like that on a non-insane timescale.
100%. Like every object in the solar system we've been to has been a surprise, right? Like this, Calypso or Io. Everyone has different geology, different physics, different dynamics. It's so exciting, as I grew up as a kid, just watching, the Voyager probes and the Mars landers, all these things we were learning was just fascinating. And it was just so frustrating that you only get like one look at them and then it's gone. And it's like, we should be sending more probes. We should be going out there, often. And we should send people out, maybe not out to the outer planets, but we certainly should be going to Mars and Venus and other places that are near.
Absolutely. It makes me happy. It makes me happy that smart people such as yourself are working on these problems, because, I feel like I say this every time we have a stream, but, the human lifespan is so fleeting that the more we can learn and the faster we can learn it, the happier I at least personally am.
Yeah, I agree. Like that was kind of the conversation that you had with Peter Beck, and 100%. And, it's super exciting that, like, I'm actually quite proud that I helped establish SpaceX, which really kind of got the party started. I think a lot more is going to happen in space now, because of commercial space doing, really crazy stuff.
Absolutely. It's almost like the start of the internet, when it's like, all we had was like Netscape and AOL, and then all of a sudden everyone gets broadband, and Google comes on, and it's no longer just like, oh, I'm gonna ask Jeeves or something. Now it's grown so much, but you can see from those little initial seeds where it's gonna go, and we have so many heavy lift launchers coming online that. Oh God, Chad is laughing at me. I think I just dated myself by saying ask Jeeves. But yeah, we have so many heavy lift vehicles coming online that it's hopefully going to be the start of some really, really interesting times here.
Absolutely.
Adrian, you have any thoughts here? Or you have any viewer questions you'd like to throw in while I take a sip of my green beverage?
Absolutely. We have a question here about potential use cases for Helios. So we talked about payload boosting, but would you also see a use case, for example, for space debris, like deorbiting or moving it into a better or like graveyard orbit?
Yeah, as it being an expendable and going to GEO. It would have to go to a graveyard orbit, because without refueling, it's impossible really to bring it back down. It's over 4,000 meters per second to get from LEO to GEO, and that's really difficult with 5 tons. So you have to reverse that for 4 kilometers per second to bring it back down, and you just don't have the juice left to do it. Now, if you had propellant depots in GEO, you could do it. Or say if you wanted to remove large space debris, like big rocket stages that have been up there forever in LEO, I would love to have this vehicle refuel in LEO, bring it, remove an object, and then stay up there, refuel again, and keep removing. So one Helios, along with propellant depots, could really, I think, reduce the cost, improve the efficiency of removing some of these big, like the top 10 objects that are a threat in space debris are big stages, are stages. So go remove these big objects.
Yeah. Why Helios for the name? What was the thinking there?
So we do orbital transfer vehicles or tugs, and that's anything from a Mira, from something that can move things around easily in LEO, or to really stretch it at the upper end. It's basically a kick stage, or really what it ends up being is like a third stage for a medium launch vehicle. And the current implementation of it basically maxes out the capability of a Falcon 9 fairing. And lift capability to take as much payload from low Earth orbit into GEO or MEO, medium Earth orbit, or to like TLI or escape. So basically, maxing out the capability of that vehicle and improving its performance a lot.
Very cool. All right, so let's just keep rolling on here. We talked about sort of why you wanted to create Impulse, and we've talked about Mira and Helios. You have another. It's another Mira that's launching again on another transporter mission later this year, right?
Yeah.
Nice.
Yeah. It's being built right now in the clean room. It's in final assembly. Yeah.
It's going to be a transporter mission, which means Vandenberg, right?
Yep.
Pro tip:
think-
if you haven't yet seen a launch from Surf Beach, they recently have reopened Surf Beach for launch viewing. So, highly recommend. You're like 3 miles away or something, which for me is like, oh my god. For you, it might not be the craziest thing. I'm sure you've seen some launches from nice and up close previously, but highly recommend.
I've seen them, and sometimes you can only just hear them because of the fog.
Yeah.
The most amazing launches out of there really are the return to launch site, because the rocket comes right back at you because it's coming in from the south and you're just north, so it looks like it's coming right at you and it turns and lands. So basically firing the rocket engine right at you as it's coming in. Pretty amazing.
Yeah, I love Vandenberg for that. Although I would be remiss if I didn't mention Surf Beach is still closed for RTLS missions because you're basically right there. So
Yeah. Right.
But yeah, so what are you? I'm being told to ask you, what are you planning to do with Mira 2, and how has Mira 1 been going? I mean, you said it's flying right now and has a burn in like 20 minutes probably. But
Yeah.
how's that whole
We're
going?
signing. We have several payloads that we haven't announced yet, but we're signing several payloads, and each of them got a different mission, doing something different. So can't really talk about it right now until they're signed and announced. But yeah, it's the manifest is filling up.
So you talked about maxing out Falcon 9's sort of lift capacity with Helios, but with Helios and Mira, you're launch vehicle agnostic, and you're trying to maintain compatibility with all of these different vehicles that are coming online.
Yeah.
Is that a significant challenge, or like how does that factor into your plans?
It is. I mean, the complications are, well, first of all, we are designed to fit inside an ELV fairing, which all of the medium launch vehicles have. So if we fit in a Falcon 9 fairing, we should be able to fit the other ones. Some of them are larger, like Terranar or New Glenn are even bigger. I'm sorry, what was the other question?
Just is it a significant challenge to sort of be
Oh, yeah.
launch vehicle agnostic like that?
But then the challenge is, of course, is that we can't. Like a spacecraft would typically be preloaded with propellant, but we've got cryogenic propellants, plus we've got almost 14 tons of it, so it has to be loaded like the other stages of the launch vehicle. That's why this is more like an upper stage really than a spacecraft in that respect, because you have to load the propellant. So you have to have propellant, the complexities of propellant loading inside the fairing. And also now you have a cryogenic propellant inside the fairing, so the thermal aspects are have to be dealt with too.
Makes sense. Let's see here. Could Helios? Go ahead, Adrian.
Just a quick, because we are having a question exactly related to lifespan. What kind of lifetime are you right now developing Helios for? And especially missions to Mars probably require a bit of a longer lifetime with dealing with cryogenics. And how you're actually what are the steps to dealing with these cryogenics, and what's the maximum lifetime you probably expect to get out of Helios between maximum time for between burns?
We haven't done that thermal yet, because that's actually happening right now. Because of that, because we have to be the tank has to be completely thermally insulated to be inside the fairing to reduce the amount of heat load going into the fairing, or heat loss basically from the fairing conditioning. It's already pretty well insulated, so that's kind of an advantage. Once you get on orbit, that you have that insulation in place so that the boil off will be minimalized. Certainly, certainly we can do a day, but I think hopefully we'll be able to be up there for days with that propellant. But if you're going to Mars or anywhere else, you do your burns, soon, and then it's just velocity there. In fact, the Oberth effect means you want to burn low, and burn hard, a high thrust burn, in low in the gravity well, and you more effectively use that energy to get to other bodies.
Could
Now, if you
Helios
wanted to land on Mars with the propellant on Helios, that'd be difficult, because now you got to store it for 8 months. So you need sunshade and cryo coolers and things like that, which are not in the plan right now.
That's one of those things I think a lot of people are wondering how that's going to go with Starship in terms of, what is going to need to be added to the sort of bare bones minimum viable product that we see now, that's going to enable sort of long-term cryo propellant storage. It's a big problem.
It is. I worked on that as propulsion CTO there. That was one of the things that I kind of initially started looking at, and it's definitely something that has to be solved, and it will make sense at some point to have propellant depots in space that the tankers fill, and sunshades and possibly cryo coolers, depending on how you do it. And that's why I said, I think it came out in one of the articles I did a couple weeks ago when we announced Helios. I said, if you've got a Starship propellant depot up there that's gonna have at least 1,000 tons to fill a Starship, just give us a sip. We'll be glad to pay for the propellant up there to keep to take our little 14 tons of propellant to hang out up there and stay up there.
Right, and I mean that also factors right back into picking methane as the fuel.
Yeah, I really think that methane is going to be kind of the oil of space, just because of most of the big vehicles are using it. Eventually, hydrogen too, because you have water on the moon, and I think that's why Blue Origin is hydrogen oriented, because they're really looking at moon resources, and that's when it really starts to make more sense. But I think if you're optimizing for LEO off of Earth, methane probably the most cost effective. If you're cost optimizing.
All right, this one might be getting into the weeds a little bit, but so I hate hydrogen, just personally, because I grew up with the shuttle, and just so many scrubs were caused by that sneaky element. But Impulse is doing a lot of stuff in-house in terms of designing your own valves, designing your own seals, all of that. Is my dislike of hydrogen misplaced? Is it really not that hard to work? I mean, I know you guys are, again, not doing hydrolocks right now, but just as someone who knows as much as like, should I hate hydrogen as much as I do?
I haven't worked with hydrogen since the TR-106, and it was difficult. As an engine designer, I love hydrogen because it's such a great coolant and such high. It makes us so well, and such high ISP. But man, that deep cryo, liquid air forming on your lines, it's just it's a pain, and it's expensive. Yeah, we purposely stayed away from hydrogen at SpaceX just because it didn't cost optimize.
Makes sense. Yeah, and methane is just kind of right there in that sweet spot. Gotta love it.
Well, when you're going to Mars, ISP really counts. So when we looked sizing that vehicle, it's like it just seemed obvious that you're going to use hydrogen because, man, you're going all the way to Mars. You want to take a lot there, so it's a lighter vehicle. But then you look at the size of the vehicle. It's actually, once you switch to methane, even though it's gone up, I don't know, 50% or whatever. I don't remember the numbers, but it goes up in mass by by tens of percent. But it's actually smaller. It's actually a much smaller vehicle because of the density. You have to have a little bit more thrust now because you're heavier, but the vehicle's smaller. And I think the cost is the same. It's just the propellant cost now, when you're fully reusable, the propellant cost is going to dominate at some point. And it just, plus all the hydrogen problems. Like, I was down at the Cape, right, quite a bit, flying the first Falcon 9s, right about the time that the last shuttles were flying. And because of that hydrogen leak they had on some of the last few flights, I never saw the shuttle fly. It scrubbed the 2 times I was there to see it. So I never did go. because of hydrogen. So yes, I also have a pain point for hydrogen.
All right, cool. I'm glad it's not just me. Here's a weird one. Do you like puzzles? Like, you're an engineer, you have to deal with all of these different trades and trade-offs and decision points. Is that something that you know is more of like a work brain thing for you, or does that sort of go in sort of all aspects of your life?
All aspects. That's why I love dirt bikes and race cars, and working on, like, I've got a little 66 Lotus in the garage I like to tinker with. I've got vintage race cars I like to tinker with. But like at work, I like to really I like to architect. Do the initial design, work closely with the designer. How it optimizes. One of the things. Like I've talked about this before, but I remember when we first flew Falcon 9 before it had really flown successfully. I remember, when we were just rolling out the pad and releasing the spec. Here's how many tons it can take to Leo. And I remember seeing on comments, maybe even on your NASA spaceflight comment blog, people saying there's no way this tiny little vehicle could throw that much. Like, the percentage of payload it could throw was very high for a launch vehicle, even the 1.0 version, and it's gotten much better. And the reason it was that way is because we all worked together. Elon was really good at optimizing everything, and I was super good at optimizing mass on the engines and performance. Like, there's a reason why the Merlin engine still has the highest thrust to weight of any rocket engine ever developed or ever flown. And it just, we were, I think, the first company ever to be able to know all of our numbers. Like when I was at TRW and we developed the TR-106, we got a spec from General Dynamics, and it has to be this mixture ratio, has to weigh this much, it has to do this, and we're just like, maybe that fits the other engine well, but it does not fit our engine. If they could just let us change this, it'd be better, or that. It was refreshing when we started SpaceX. It's like, oh, the engine thrust needs to come up a little bit more. We can change the mixture ratio here. You're optimal. You know the cost per pound on the first stage, on the second stage. You're just able to optimize everything. Whereas traditional aerospace with layers of suppliers, like, you get a spec for a valve. Like, this is a typical thing, and we could talk all day about valves, but you get a spec for a valve. Like, say it's a big valve, like 5 pounds, and you're just thinking, oh man, that's kind of heavy. We could probably make that 2 pounds, but because you want to take it easy, make money on it, and not spend a lot of time on it. You do it. It ends up being 4 pounds, just to make sure you have some margin. So right. Everything ends up heavy. Ends up heavy. And then, of course, cost plus fixed fee, it ends up being expensive. We were the first company to develop a launch vehicle to not do that. Now, I'm sure, the original ICBMs were very optimized and stuff, but then I think they when they became launch vehicles and this spec thing happened and different companies providing different things, they just lost that ability to really optimize the hardware and get everything out of it. And then now, Starship, to the extreme, and like the Raptor's an incredible engine, and the things they're doing on that vehicle, just further optimization of chemical rockets.
I love to see it. Speaking of optimization, I have to ask this. Recently on the Merlin, we have seen a different nozzle that we refer to as the stubby nozzle, and there are sometimes on NSF you watch our stuff, so we like to do little tribalisms for fun sometimes. So I hate the stubby nozzle because I think it looks cursed. I understand. I don't actually hate it. It works. It's a good design. It's optimized for a different thing than just sheer ISP. But all that said, Tom, stubby or not stubby?
I of course love the full nozzle. It was very difficult to develop, but what an awesome piece of hardware. But I understand, with supplier problems, and it's it's just diminishing returns. Like, the more the more area ratio you get, the less percentage of performance you get. So you can cut off a lot of that, area, which is mass, and also it's thinner. As it gets out there, it gets thinner, and the thinner that material is, the cost per pound goes up a lot, because the way they process that material is every time they roll it to thin it, they have to heat treat it, and this is a very high strength material at temperature, so you have to get really hot and inert. You can't have any oxygen. It's got to be like in argon, and you anneal it. So it's super expensive to keep rolling it down thinner and thinner and thinner. So that last few feet of that nozzle are the most expensive, and they're pretty heavy because of the area. So it definitely, I can see where if you don't need that performance, and you're having a hard time, meeting supply chain because you're flying so often, and there's a reason why it happens.
Yeah, it makes sense. It's the materials. Oh God, am I gonna say this right? Niobium? I don't even know how to say that word.
We call niobium. We used to call it columbium, which is not even right. And really, like the industry called it columbium. And Elon said, didn't they change the name of it like in '77 to niobium? I go, yeah, they did, but everybody still calls it. He goes, what's wrong? He says, just call it niobium. So we just started calling it niobium. And really, the industry changed now because we fly so much of it. It's kind of the old rocket guys were calling it columbium. Well, it's time to call it the right name.
I had no idea. Wow. Nifty.
Yeah.
Adrian, what have you got for us, good buddy?
Yes, I will take a lot of questions here about your favorite engines and everything and combine them, because there were like a lot of questions here about what do you think about nuclear, what do you think about rotary engines. So I'm just combining them in one single question here. We've seen a lot of new developments in engine as of late, full flow stage combustion, of course, 3D printing, aerospikes. Which technologies of these are exciting you, and like what's your favorite if you have to pick one here?
Oh boy, I don't know that much about RDEs. Rotating detonation engines. I think that could be very promising because now you don't have to have crazy turbo pumps to get high performance. But I'm not a big fan of aerospikes or annular engines, just because the amount of area you have to cool, it just really, especially on an annular aerospike. I've looked at them. We've designed them at TRW, at SpaceX, and it always comes up that you've got so much area to cool. Unless you're running a low enough pressure where you don't need film cooling, you pretty much end up losing on combustion efficiency much of what you gain on CF efficiency. And also they're hard to make. They're an annular pressure vessel is difficult to make. So I was never that convinced. We did some studies when I was at TRW and of the CF, and the CF efficiency wasn't as high as it is on regular Bell, so you lose a lot of what you think you gain theoretically. So I'm not a huge fan of. Never have been a huge fan of aerospikes.
Sorry, Tim.
Tim, somewhere I want to get the real numbers, but maybe I'm wrong. I think
somewhere,
you need really great coolant.
So there was a point in, for example, at SpaceX or like in general in your rocket paths where you looked at, for example, at aerospikes, and where you looked at them, you were try to build manufacturing pathfinders, and then you came to the conclusion, yeah, it's not the time yet, or it's not for you.
Yeah, we've looked at everything. We've looked at what was the TAN, the thrust augmented nozzles, where you inject propellant in the nozzles that Aerojet had patented, or we looked at that a lot, and that didn't make sense to us either. It was close, that people could make that work, but it just wasn't going to help Falcon or Starship.
What about nuclear?
Sorry?
Like nuclear engines.
Oh, nuclear. Yeah, that would be cool. I think I'm too far into my career to start on a new technology. Somebody needs to carry that forward. You're talking about doubling ISP. Somebody's really got to get the weight out of those. You kind of lose so much of what you gain because the engines are so heavy. The thrust weight's like single digit, like 7 or something. I think that it's gotten a lot better, but that's a pretty cool technology. It's only going to work in space though, because nobody's going to let you fire a nuclear rocket engine, launch a nuclear rocket engine off a pad.
Right.
Yeah, I think we would all prefer that, to not have nuclear engines launching off pads in the near future.
And what was that, like Project Orion or something? That was like a nuclear aircraft that just belched. Yeah, no thanks.
Nuclear, like a fission reactor or a fission engine, being launched on a space is actually safer than launching RTGs. I didn't realize that, but plutonium used in RTGs has so many more curies of radiation. I've already reached the limit of my knowledge of this, but working with guys that are way smarter, like once you have a reactor that just has uranium in it that hasn't been run, where you end up with all the really crazy actinides, it's actually pretty damn safe. And if you crash and that fell in the ocean, went to the bottom of the ocean, just leave it. It's not, they'd probably go get it, but you can just leave it. It's just going to sink into the bottom of the ocean. It's not really going to do anything. Even if it went off, it would probably boil some water for a while, and then it would burn out and just stay there. So, whereas plutonium is some crazy stuff. So I'm probably going to get all kinds of comments about talking about something I don't know much about. But from what I've heard, like from a launch safety standpoint, launching a fission reactor, like either a space reactor for power or a nuclear thermal with a fission reactor is not that big of a deal.
I hope we get there at some point, just because, for the same reason that Helios is so cool and in enabling technology, something along those lines. It feels to me like so far in the future, but eventually you got to figure, it'll happen. So something maybe to look forward to.
I want it to happen. I think my young engineers, it's definitely like the future that impulse space needs to continue. Like we just want to open up, the space era, like, and that's going to involve, like, we need to develop the warp drive at some point, right? It certainly will probably be. I'm going to start it and max out space chemical propulsion technology, and then my guys can develop the next thing. And this is where we need a lot of help from NASA. I think NASA should be spending their budget developing these new technologies rather than trying to compete with the guys building rockets.
Yeah, wholeheartedly agree
here.
I
know that NASA wants to do that too, but I don't think Congress is letting them.
Right. Let's see here. So you mentioned you have quite a car collection. How has your love of automobiles and Porsches and everything, how has that sort of translated or influenced like your rocket engine design work?
I think I'm just kind of like a heat engine guy. I loved the internal combustion engine. I remember in 6th grade, for some reason in the grade school library, there was a high school level internal combustion engine book, 4-stroke and 2-stroke cycle. And I remember that book where you had to sign your name to check it out. It was just all my name, because I just check it out and keep checking it out. I had that book for like a whole year. And my dad was explaining how valves work. I just was fascinated. I took our lawnmower after that. I took the lawnmower apart and put it back together. We had dirt bikes in Idaho, and we would try to modify them. I've always been an engine guy. I had a steam engine. Where's it at? Oh, it's in the other room. I have a steam engine that I got when I was 12 years old for Christmas. I still have. I used to run that every Christmas. It's a little tiny toy steam engine. So I've always been an engine guy. And then of course, the Estes rockets and the Centurion, I think, rockets were the ones I first bought when I was a kid, were just fascinating to me. But what it really, I think, being like a gearhead, I guess you'd say, and like my first car was a sports car. I bought a Triumph Spitfire as my first car in Idaho, which is like a stupid car to have in a place that gets water. But when I became a mechanical engineer and got into college, and that's when my fascination for liquid rocket engines. Once I understood like how you could design them, like fluid dynamics and combustion and chemicals, all together, a mechanical engineering degree is almost a perfect degree because you use everything you learn. You absolutely use on a rocket engine. So it was just like, man, this is what. Then I knew this is what I'm going to do. I'm going to be a liquid rocket guy.
Nice. Oh my gosh, that's beautiful. What is that? That's
a great investment.
That's a Porsche. What type of Porsche is that?
That's a 2010 GT3 RS. That was my first 911. I bought that when it was less than a year old. The guy was buying, the next best thing, so he flipped that car. It's worth almost 3 times what I paid for it, and it's got 10 times as many miles as when I bought it. Just leave it at
That never happens.
It's basically a car. It doesn't happen that often. It's the last version of the GT3 RSs, which is their top performing 911. It was the last version that came with the 6-speed manual. Now they have the PD, the paddle shifters on them, the newer ones. So these cars have really held their value. Great car to own. Really, really nice driving car, and it looks fantastic, I think.
So, is there? This might be a stretch. Is there a rocket that you would say is most like a Porsche 911? Because a lot of people consider the Porsche 911 to be like the canonical idea of a sports car, like the pure essence of a sports car distilled. Is there a rocket that you would sort of liken to a rocket version of that? I mean, I guess the obvious answer is Falcon 9.
Yeah, I think it is Falcon 9. I was going to say because I see Porsches. They're not the most expensive supercar. They're just the best, right? They're just like that GT3 RS will destroy cars that cost 5 times as much on a track. It's just they're so efficient. They're kind of unbelievable how. That's why somebody when I bought my Ferrari, people go, "I thought you were a Porsche guy." It's like I'm a car guy. I just have a lot of Porsches because they're such efficient race cars and fast cars. So, and I kind of see the Falcon 9 that way. It's just really an efficient, just does its job really well.
Extremely well optimized, yeah.
Yes. Yep.
Adrian, what have you got for us, buddy?
Yes. Next question I want to ask here is, it's a common misconception or like a common idea we have about rocket engines. I want to ask you if it's actually true. And that's if we always think that a rocket engine has less wear and tear if it'll run slower. So is that actually the case? Can a rocket engine run longer or run more often if it only has to do like 90% of its thrust? Or is that not an assumption we should make?
The time really counts in the turbo pumps, mostly like blade cracking and bearing wear, and certainly like on a staged combustion engine, it's the power head pressures are so nonlinear to PC. Like say if you increase PC 10%, the pump outlet pressure, so the amount of power that you have to put through the pumps will maybe go up by 20%. It's nonlinear. In fact, it goes vertical at some point. You can't, like Raptor's there, like for every psi that you add to main chamber, you have to add tens of psi to the outlet pressure of the pump. So at some point you hit the wall, and then you just keep getting a little bit more efficiency so you can get more out. So yeah, that's true on components, but really on the combustion chamber and the injector, it's mostly about thermal cycles because things get very hot, and they get so hot that they're going to plastically deform. So it's kind of like bending the paper clip. It's just going to crack at some point, but you're bending it with heat, not by movement. So that's how like combustion chambers crack, injectors fail. It's just by a thermal cycle. So there's a time problem, and there's certainly a cycle problem. Like our safe, the little 5-pounder that we fly on Mira is, I think, is just cycle life. It's got an oxidation life that could be hundreds of hours for all I know. We've never run it that long, but it, after tens of thousands of cycles, it cracks.
Makes sense.
Thank you. And there's another question I want to ask because we talked about methane before. There was a lot of like, if you search for why was methane not used until now, there's like millions of answers of different, like even different answers. Like, what's your take on this? Why is methane not like? Why was nobody like using it in the 90s or 80s on a rocket or 70s?
That's a good question. You could I had a company I helped way back in the 90s do the MOX box, where we mixed methane and oxygen to make a monopropellant. We did this Air Force SBIR, and you couldn't get liquid methane then. We had to, you couldn't just go buy it like you can now. I don't know if that was really the problem, because you could always get liquefied natural gas. It's just I think just because the launch vehicles, the Atlas vehicle sat in a silo, they only wanted to load one propellant, they didn't want two cryos. Who knows? You started with kerosene, maybe because it was a military thing, they just wanted something that was easily transportable. It wasn't optimized to be a launch vehicle. It was optimized to be a weapon first, and then the engines all got developed for that propellant, and that carried through history until somebody said, we're going to optimize now for cost and efficiency of getting to LEO, or to high energy orbits, as a commercial company, and then you start making the right decisions on which propellant to use.
Got it. Thank you.
All right. Let's see here. So let's go back to Helios for a second. So far, the website for Helios does not list a specific impulse. Do you already have sort of a ballpark on that? Is that something we can sort of talk about?
I mean, I hate to put out a number until we run the engine, until we demonstrated it, but I can tell you this: if we're going to be running close to, we kind of analyze and figure out we'll be able to run close to 99% combustion efficiency. That's the great thing about this cycle is you're running gas in the main injector, which wants to mix. It's pretty stable. We have a lot of history running these types of engines now because of Raptor, a gas coax injector. So we know we can get pretty close to 99%. So anybody can do the numbers. 99% combustion efficiency for these propellants with an area ratio of whatever it's at, 160. It's actually, we started out at 200 and we've actually cut it just to get more volume, some more optimization. It could be bigger. It's 375-ish seconds. I think a little bit more than that, but we'll lock that number in as we go develop the engine. Hopefully it can do better. Maybe we're sandbagging a little bit. Maybe we're missing it. Might be 370, might be 380.
Very cool. It's a staged combustion cycle engine, right? Is it full flow, oxygen rich, fuel rich?
I'm glad you asked that, because that's a great discussion. It's not full flow, and there's a reason why I don't think it makes sense for a space engine to be full flow. It's ox-rich stage combustion, which seems like the perfect cycle for an engine like this. Full flow is when you need to get as much chamber pressure as possible, which is a booster engine. Especially a booster engine that you want to take as much payload to Mars as possible. So that's why Raptor, has crazy high chamber pressures. That's why the RD-180 has crazy high chamber pressures.
Right.
Or the Space Shuttle main engine to run as big a bell nozzle to get that your performance is your pressure ratio from PC to exit pressure. Well, at sea level, your exit pressure is 15 psi. So you can't get a high ratio without going high on chamber pressure. In the vacuum of space, you're dividing by zero, right? It's zero exit pressure. So you can put as much nozzle on the engine as you want. And then it just becomes how much will fit and what's the diminishing returns on it. Like I said, the Danab engine, for Helios originally was a 200 area ratio, but then we started looking at the packaging and said, we don't gain that much on that extra 40, so let's cut it to 160 or whatever it's at now to fit better, and we could still throw the payload that's out there. So, and the reason it's ox-rich stage combustion is, of course, it's stage combustion because you want to get all the performance. This is a third stage, so performance is ultimate. Like every stage, just requires, the rocket equation gets harder and harder with every stage.
Right.
So it's going to be stage combustion. It's just the right cycle. And ox-rich is nice because all of the oxygen goes through the preburner and then through the turbine to drive the pump. And so you have this big pressure drop across there. And then only a tiny amount, like a few percent of the fuel goes into that preburner. And the rest of the fuel is coming out this crazy pressure, and you can use it to cool the combustion chamber. So you have a pretty, a very advantageous ratio of combustion pressure dropped to actual combustion pressure, which means you don't have to run film cooling. That's so well cooled because you can run so much velocity through your channels that it's just a great cycle. And you pick up a lot of heat in that combustion chamber, so that propellant is pretty warm coming through the injectors. You got hot oxygen from your ox-rich cycle, and you got very warm methane on the fuel side, which just it mixes really well in this injector. And because you don't have droplets, like on a liquid rocket like Merlin, you don't have this combustion instability problem. There's still things you got to watch out for and design for, but it's nothing like the traditional stability problems you have with liquid propellants. And at throttle, you can deeply throttle it. There's just a whole bunch of advantages to having this type of setup.
Yeah, makes sense. And no film cooling, so you don't take a hit on ISP or waste any propellant doing all that too. So
yeah, that's one of the great selling points again of using methane and especially hydrogen. It's such a great coolant that if you do it right, you can not have to run film cooling and not burn your walls and also have really good cycle life.
Nice. Adrian, you got something for us?
Yes.
Is it about
Effort.
hydrogen engines?
No, it's about orbital. Well, actually, it's partially about hydrogen engines. It's about orbital accuracy because there's a lot of talk, especially on the internet and discussion forums, about that high energy second stage and third stage engines have the reputation of sometimes maybe not being able to precisely insert into an orbit, because the assumption that people make is you're getting into danger of overshooting. So what's your take on this? Do you really need a low energy engine to precisely insert into orbit?
No, we used to worry about that a lot with MVAC, with Merlin vacuum, because it's a gigantic last stage engine. It's the current MVAC, what is this, 220,000 pounds of thrust, and it inserts accurately. It's really understanding your cutoff impulse. You give that thing the kill signal, shut off, knowing how much propellant's in there and burning, and how much cutoff impulse you have, so you can time it perfect and hit it. It's certainly going to be harder to hit, the bullseye than say an RL-10 or something that's only got 20,000, 1/10 the thrust. But compared to an MVAC, we're down here at 15,000 pounds. Of course, we got less than 1/10 of the propellant on board, but we can throttle deeply if we really want to hit it close also. And if somebody had you got to hit within a tiny fraction of a percent, we can always throttle way down and do that. But I'm not too worried about it. I think we can hit that cutoff impulse really, really accurately.
Nice.
So not a worry, and as long as you understand your engine, it works with a lot of thrust as well.
Yeah.
There's another question here I want to ask here, which I'm getting a few times here. How many times have you strapped a rocket to a race car?
Let me show you a picture. Hold on a second.
Oh, I'm excited for this.
I almost strapped a rocket to a race car. Can you see that?
Wow. Is that the Bonneville Salt Flats?
Yes. So about the time or even before I left SpaceX, some guy I knew wanted to do a land speed record car and had some sponsors, and knew some people and wanted a rocket engine, so I went and helped him. And then COVID happened and nothing happened. And I'm glad it didn't, because I'm glad, I went and did something useful to the world. But it was really cool because I designed that whole thing. I actually have that whole car in SolidWorks on this computer right here. I designed the whole car. And it's very comparable to the Blue Flame, which held the land speed record. It last one to hold it in America for 13 years. The Blue Flame had, it was supposed to. I'm not remembering the numbers really. I think it was supposed to be like a 22 or 25,000 pound thrust engine, but because it ran peroxide and methane. To get sponsorship from some energy guys, the Blue Flame. But when they ran the methane, the bipropellant, they would burn the engine out. So they just ran just enough to claim that they were burning it. It was mostly just a monopropellant peroxide engine. So it was only running like 11, like half thrust or like 13,000 pounds. I don't know. You can look it up on Wikipedia. So, but it's still, the car went, and that engine weighed 700 pounds. So here I come with basically a LOX kerosene engine. It made sense for this to use kerosene, because you could pre-tank it, or you could load it really fast and just load the oxygen. You have to load again to come back within an hour. So the oxygen tank's already cold. We're going to roll the truck up and refill it, so it'll fill fast. And you pre-measure the fuel and just pump it in, and it's ready to go. So and you press up and go back. But my engine, if I remember right, weighed less than 100 pounds and made 30,000 pounds of thrust. So this thing accelerates at 5 Gs just to limit the damage to the driver. Because it turns out, I learned a lot about it. You're really limited in where you can run, because it takes you, it'll take 3 miles to get to the start of the mile. And right. Then, so now you're 4 miles out when it's the average speed to the measured mile. And then you start throwing out parachutes, reefing a parachute to slow down, which, depending on how many times you stage it, because of the nonlinearity of drag by v squared, it can take a long time to slow down. Brakes are almost useless because you're on dirt and they'll overheat. So you got to use parachutes. So just finding it, you need 10 miles really to have margin, but I could do it with this thing if you had really good parachutes, maybe in 6 miles or 7. But we were going for 1,000 miles an hour, so Mach 1.4 is what we wanted to do. So it was going to be really cool, but it had a non-zero chance of killing somebody, so I'm just glad we didn't do it.
Yeah. Yeah, a lot of people don't know, to get that speed record, you have to do it twice in a short period of time. Which is archaic, because back in the old days, the cars were only doing 100 miles an hour, and the wind made a big difference. So the wind doesn't make a difference at all anymore. So really, they should just ignore the comeback thing. It's just one run, and makes it much easier, especially if you're loading a rocket engine. Oh man, and I could go down this rabbit hole for a while, but I will spare our non-car friends.
I always say there's nothing to rather talk about than rockets and race cars, and in this case you combine them, so it's the ultimate, right?
Nice. Adrian, do you have another one?
Yes. We have one question here about Helios, which is, why did you decide for going for methane over, for example, an ion thruster? Isn't moving stuff from LEO to GEO much more efficient with an ion thruster, like using argon?
Yeah, except we're eliminating ion thrusters really, because the standard way to get to GEO right now is to go GTO, geosynchronous transfer orbit, and then using EP, electric propulsion, to round out the orbit and take out the inclination, which is about 15 to 1800 meters per second that you left, and even with tens of kilowatts of power, that still takes 6 to 8 months. And that's your highest revenue, the first part of the mission. These guys are in a hurry to get up there and start getting revenue. So to do it from LEO and have to do 4,200 meters per second, it's actually worse than that, because you're not doing Hohmann transfers, you're spiraling up. It's not efficient. and you're going through the radiation belts, through the Van Allen belts. So now you have to design your spacecraft to go through the worst radiation environments on the way. So it wouldn't make sense. So what we're doing is getting you there in a day, like in 2 burns. Like, you do the GTO burn, and then you do a second burn that burn takes out both inclination and circularizes. So in 2 burns, you're there. So it's like, I don't know, 6 or 8 hours, and you're on station, and commission your spacecraft and start earning revenue.
Yeah, that makes sense too, because then you're able to use the tug to tug things more often, rather than having to wait a long period of time for an ion engine to do that circularization and all that.
But I'm a huge fan of EP. I led the original. I'm the one that spec'd the original thrusters for Starlink. That was the first thing Elon asked me, I think, when I became Propulsion CTO. He says, "What propulsion are we going to use on Starlink?" And I said, "Probably be Hall effect thrusters." He goes, "No, go do the study. Everything from cold gas to ion." And it came back. Guess what? Hall effect thrusters. And that's the right technology for those spacecraft. It's the right technology really for a spacecraft that's going to stay in geo for a long time. It's the right technology to go to the outer planets if you're not in a hurry, like a big electric tug on top of a Helios, on top of a Falcon 9 or a Vulcan, could get out to the outer planets really fast. Take years off of the typical ones that are going now. So
I love the sound of that. I love it. Okay, so you mentioned SolidWorks. Is that like, what CAD software do you use? What do you design rocket engines with? It's like so beyond my realm of knowledge, but I know people design things in 3D on computers.
Yeah, everybody's using NX, and Impulse is, SpaceX is. It's kind of the industry standard. If you tried to put a whole Falcon 9 into SolidWorks, it would lock up. I think if you put a whole Merlin engine in SolidWorks, you might have a problem. So I use SolidWorks. It's really easy and it's affordable. And I know enough about using NX to be dangerous. I can pull up models and look at them and do simple things. But I'm pretty good at SolidWorks, and I use that at home. It's great for just designing stuff quick. But I did all the initial designs of the rocket engines and stuff in SolidWorks, so the guys are kind of mad at me because like, oh man, you did in SolidWorks, so they can't take what I did and exactly use it because it doesn't translate over.
Right. Neat. Let's see. What, Adrian, do you have another question? I don't have one in my quiver right off the bat.
You have initially developed Oh, go ahead.
You didn't ask me about the propellants that I use for Mira and why. I thought we'd get into that discussion about hypergols and why not.
By all means. I mean, spicy orange cloud, scary, but let's talk about hypergols. Let's talk about what your choices and trades were on Mira.
Yeah, but I worked with hypergols a lot at TRW. That was really the main propellant that we used there. I was lucky that I did development my whole time there. Never got on a flight program, and so I ran every propellant that existed, including nitrogen trifluorides, like some really crazy propellants. And back then the allowable limits for both nitrogen tetroxide and the hydrazines like MMH and hydrazine were 10 times higher than they are now. They were 10 parts per million, and now they're 1 part per million. And so you could smell it, like at our test site, you could smell hydrazine. It smells kind of like fishy ammonia. You definitely, like, something's wrong here. Something smells bad. But if you smell it now, it's too much. So when we started SpaceX, one of the questions asked early on was like, hey, what about the second stage? Like, you want to use storables? And I said, no, no. The cost of safety, it's just, they're so corrosive. There's really no soft goods, meaning, like Teflon or O-rings that are truly compatible with it. Like, it just tears up everything. It forms nitric acid when it gets water, so it just corrodes your valves. I think that's like the Starliner problem. But we did use it on Dragon. So this engine behind me here is a storable engine, is a Hypergol engine. But I knew that Hypergols are expensive. They're hundreds of dollars a kilogram. So they're the cost of safety to use them. Like you have to go way out in the desert. You have to get all kinds of permits to run it. It's really hard. You got to convince the companies that make it that you're a real rocket company to even buy it, because it's such a pervasive toxin and it's such a dangerous propellant. So I knew that with the cost of access to space going down, that the days of using that are going to end for Hypergols at some point. It's just there's got to be something else out there. And this has been the holy grail. If you've read the Ignition book by John D. Clark, which I'm sure a lot of your followers have read because it's such a great book. And if you haven't, go read that. It's hilarious, and you learn a lot. It's just hard to replace such a high density, self-igniting, high performance propellant. So the next best thing that I could find is nitrous and ethane. So if you look at those two tanks on that Mira spacecraft there, the bottom tank is nitrous, and the top one is ethane. Ethane is the hydrocarbon in between propane and methane. So it's a liquid at about 600 psi. Nitrous oxide, a liquid at about 700 psi at room temperature. So it's self-pressurized, and the little. I wish I had one of my little 5-pounders here. I work. I always have it on my desk. I can hold it up and show you the little safe engine. You can see the pictures online, but it's 295 seconds of ISP. And if you just search for like Aerojet Rocketdyne 22 Newton thruster 5-pounder, it's 305 seconds of ISP. So we're right there. We're just a few percent away on performance, and the cost of that engine is so much lower, and the cost of safety is just like could be an order of magnitude lower to use that propellant. So it is not as dense. The tank pressure's higher, so the tanks are a little heavier. So it's not going to be as ultimate performance, but it's good enough. Mira can hang out for years on orbit. It's completely storable in space. Space tends to be cold, so you can actually run it at lower pressure and solve the tank pressure problem. You don't have to run a helium system and have a high pressure helium valve like what I think is what failed on the Peregrine moon lander. So you eliminate a whole system and some failure modes. So I think it's the right propellants if you don't need ultimate performance. And then if you need ultimate performance, then that's where Helios comes in, and you go cryogenics.
Makes sense. Oh man, it's so weird to think about what hypergols smell like, because everything I've ever read or learned is like any amount of it whatsoever, you're gonna have a bad time. But if it's like 1 or 10 parts per million, you can smell it. You're not gonna die, or your lungs aren't gonna fill with fluid or something. But just the idea of like, I'm smelling a hypergol, I just ugh. No thanks.
You could I remember we would take the engines down to the test site when I was at TRW 30 years ago, and we'd clean the engine on the test stand and dry it out and nitrogen purge it, and you bring it back to the office. You have a box full of parts, and you open the box like, whoo, because just the O-rings would soak monomethyl hydrazine or hydrazine. I ran both, and the O-rings would stink. So you could take all the O-rings off and throw them in the garbage can right there in your in your office. Like we were pretty lackadaisical about it back then. I'll probably die of liver cancer or something because of all these years of working with these propellants, but it was not that big of a deal back then. Now it's a big deal. Like, oh, we smell hydrazine. Red alert! Everybody evacuate the building and bring in the hazmat crew. Right.
Simpler time.
Yeah.
Oh man. Well, we're coming up on. We got about 10 minutes left here, so I think this is a good time to just say if there's anything that we haven't hit on yet that you'd really like to talk about, or that I should have asked you but I'm too stupid to have asked you, such as the excellent Mira question that we just did. Is there anything that you'd like to hit on that we can can hit here before we get into the end times?
Oh man, boy, we were everywhere, right? We covered it pretty well.
Excellent. Well, if you think of something in the next 10 minutes, feel free to jump in.
I have one.
I was about to say, and Adrian, speaking of jumping in, by all means.
So there's this Mars mission together with Relativity, right?
Mhm.
Regarding your 2026-ish Mars mission with Relativity together, what's the status? Has hardware been built? What critical milestones are up? Like, give us, if you mind, like an overall overview. Where are we on that mission?
Yeah, we were, that was the first mission we signed. Just months after I incorporated Impulse, we got approached by Relativity. Hey, let's do this Mars mission. Which, of course, we're like, yeah, that's really cool. Let's do that. Like Peter Beck talked about doing Venus. That this is my thing like that. Like, this is something I want to do. I don't need to make money at it. Let's just go do it. Yeah. So you got the video rolling of this thing. So, and the plan is to use, like, what you see right there is the same size, and shape of the reentry vehicle, the aeroshell that was used for InSight or Phoenix or those medium-sized Mars missions. So, and same parachute. So everything that NASA developed to get through that, their 7 minutes of terror,
Right.
we would use. I do not have the resources or the time to reinvent all that. But that right there, what drops out of the is new. That's us. That's our engines. The Rigel engine, which you saw at the very beginning, running, that nice blue Mach diamonds. That's 180 pounds of thrust in vacuum. The Rigel. So those are completely throttleable engines. Linearly throttleable. So you can it's basically like a quadcopter. You can just land this thing and steer it. And the way they're canted, you can do a 6-axis of control. So we have the hopper that we built. We were moving pretty fast on this because we're trying to make the the 2024, like, end of this year opportunity. But it turns out Terranar wouldn't be ready in time, so we moved it out 2 more years to the end of 26. So we got time. So we focused more on Mira and haven't been working as hard on this, but we got to pick it up again now later this year in order to make the schedule. Super excited about it. I hope there's a market for it. We would really like to help NASA get there, and anybody else that wants to take a payload, universities, other countries that want to take payloads to Mars, or commercial companies, even advertise. We had somebody ask, hey, would you take one of those little bottles of vodka, to set it on Mars and take a picture of it? Like, yeah, sure. Put it on there. Yeah. So
Nice.
we're looking for a way, to make this something that, like, every cycle we do 1 or 2 of these and try to optimize how much payload we can get in that standard size mission that that NASA's kind of developed, that standard aeroshell.
Right, because there's a lot of heritage on sort of that EDL system.
That's part, and also the deep space navigation is really tricky. They've got that down. We want to use that too. Have a small landing ellipse and hit right where you want to be.
Cool
And
deal.
we've actually told NASA. We said we'd be willing to do, take it further, like land in tight places, like have object detection capabilities, hover for a while and find a place to land between rocks or deep canyons, like stuff that they may not want to do, because it's too risky. We would love to go to places where they may not want, or try to land high. They usually try to go pretty low in the atmosphere because parachutes don't work when it's really rarefied.
Right.
We'd be willing to take more propulsion to fight that, and be able to land it in the highlands where they've never landed. So anything that they would like to do, but it's too risky to take to headquarters or whatever, we would love to do it.
I mean, that's perfect for a commercial company. That's
Yeah.
the sort of thing that is tailor-made for NASA to not do, for all the reasons you said.
Yeah, it's like you guys have developed this technology and made it work. So let a commercial company take it, the next step further and do more risky things with it, and try to get the cost out by trying to do the same thing over and over again, where you're going to go off and develop new things rather than make another cookie cutter of the same thing.
Yeah. All right. Well, is there anything you'd recommend for up-and-coming aerospace engineering students in terms of like things to, what courses or what maybe extracurriculars to get into? I mean, I know SpaceX famously hires a whole bunch of Formula SAE people out of college. I know that's like a good sort of feeder route to get in there. For Impulse, any recommendations for folks that might be in,
like the structures guys, and we did too, like people that did the Formula SAE things, or they have a bunch of those now. There's the Baja ones. There's a bunch of different ones. We would often hire people. There's a lot of rocket engine programs now. It used to be mostly just like Purdue, but now, there's a lot of people doing liquid rocket engines. So we look for people that have led those projects or led parts of that, because GPA is not enough. I mean, we have really smart people that just don't have common sense and can't design their way out of a wet paper bag. So it's like really somebody that's, that's shown that they can lead a project or design something really cool, even if it's just something you did on your own. Like, I designed this computer-controlled robotic gizmo that did something really cool. Like that's what we look for. It's like somebody that can come up with some really cool thing out of thin air.
Neat. All right, well, I think as we get close to the end here, it's time for me to ask you if you have a favorite sort of career event, maybe a favorite launch or favorite space-related story that sort of occupies a special place in your mind.
I think all of my favorite space-related stories have been told in Liftoff or the Ashley Vance book, or certainly in the upcoming what's it called? Touchdown? What's the
re-entry? Something like that.
Re-entry. Yeah, I know it's coming back. Something. So I think I've told all my great stories.
No worries.
I probably haven't told some of the TRW stories from way back in the day, but we don't want to go back that far.
All right, fair enough. But all right, well, Tom, thank you so much for spending an hour and a half of your Sunday with us chit-chatting. Adrian, do you have anything before we sign off here?
I just want to also thank you, Tom. That was like such a pleasure to really have this conversation for 90 minutes, and I can tell I learned a lot today.
Yeah, it was fun. Thanks, guys.
Yeah, anytime you want to come back, just let us know. We would love to talk more about Impulse, especially as you get closer to Helios, and especially as you get closer to that Mars mission.
Okay.
Awesome. Well, once again, thank you on behalf of NSF and all of our viewers, and we will look forward to talking with you again. Thank you to all of our members, and especially thank you to our launch directors and flight engineers who really are the bedrock of everything that we do here. So thank you, everyone that supports what we do. We hope you enjoyed this week's episode of NASA Spaceflight Live. But I think with that, we will let y'all nerds enjoy the rest of your Sunday. Once again, Tom, thank you so much. That was a lot of fun.
Thank you, guys.
And here we go. We have liftoff.
Propulsion continues to be nominal.
R68 chamber pressure looks good.
Doubling up. SPD off. Bring in SPD off. Off. It's orange!
125! Oh my god!
Decollage. Put that in the big bag,
343 unfolds to go.
Indeed.
We rise together, back to the moon and beyond.
The methane would be igniting the flare, correct?
Yikes. You dead? Sure. We don't need any more of these.